Okay, let's start. So the second lecture by Javier.
Hello, everyone, again. The time has come to see the beautiful cosmic pie that we have been preaching about. You can take your piece to accompany your coffee. A bit of dark energy, perhaps. One of these slices of the 25% of dark matter, or perhaps something more standard flavor, like your baryons. Now we have this very nice, after all we have argued, Kafir and I, we have argued to give you the numbers, the composition of the universe in terms of energy, and now you have it there. At least you know the big part. This is just more subtle and not that important for these lectures. So I wanted to continue today with a couple of evidences which I think they make very strong points, or well, they make more points of more strength to consider the existence of dark matter. So some people would call them evidences for dark matter. But before that, I just wanted to show you a little bit to set the stage a little bit of the universe, because I've been patching physics in the universe in the galactic scale, galactic clusters. Then I moved to BBN. Then we spoke about the CMB. I just wanted to show you a little bit how this cosmic pie evolves as a function of redshift, so that you can just place yourselves and travel through the history of the universe. So here, in this diagram, I'm showing you the composition of the universe as a function of redshift, for you to feel comfortable in our trips forward and back in time. So here, this should be redshift. Sorry, this should be redshift. So we are living, we are all now at minus infinity, because this is a log scale. And so this is the cosmic pie I showed you before. It turns out that nowadays the energy density of the universe is dominated by the cosmological constant. Essentially all these supernovas and galaxies, standard candles that we have used to measure the different ingredients with this luminosity versus redshift curve that I showed you, are more or less in this region, okay? So we can actually see the transition between lambda and the dark matter. This 30% of the universe nowadays, okay, 30%. Of course, as the redshift goes, as the universe compresses, the amount of dark matter, so the density, okay, the density increases because the volume is decreasing. And it becomes dominant very soon at around, you see, redshift of order 1. Most of the energy of the universe now is in the form of dark matter. The cosmological constant is just a small contribution. Recall that this is normalized to the total, so that the sum of all components will be 1, right? And the universe, for many units of redshift, so as we are compressing the universe more and more, the universe still seems to be dominated by the dark matter of the universe and by the baryons, that here I just show you as a dashed line. But then, at some point, the radiation of the cosmic microwave background and the neutrinos that we know are there, they contribute a miserable, completely ridiculous amount to the energy density of the universe today. But as we compress the universe, considering earlier times, their relative importance increases, because as we compress radiation, we are increasing the energy of each of the particles. Okay, so this increases, and at a redshift of something like 3,000 or so, it becomes comparable with the energy density stored in matter. Okay, and from this moment on is when so we are in the period of the universe where the expansion of the universe. Remember that the energy density sets the expansion rate. The expansion rate of the universe and most of the energy in the universe is in the form of radiation. This is what we call the radiation era. Radiation-dominated expansion, matter-dominated expansion, and cosmological constant-dominated expansion. These are the three epochs that we might be speaking about. At some point, if we go very, very, very early in time, we might find we will have a period of, we think that there was a period of inflation and reheating. So this is very, very, very early cosmology that I will only be talking about it later. Very good. So accidentally, we can also put another event. We have to put another very important event in this graph, which came to us for free when we measure the baryon density of the universe. It is the release of the CMB, and we can just understand it again by just noting that the proton density is going to be more or less similar to the electron density, right? And we learn from BBN that this is a very small quantity. And this is again, the smallness of this quantity is going to be very important to determine the state of electrons in the universe. Okay? So as we go early in time, the photons become very energetic and are able to, all the photons in the CMB, they're able to ionize all neutral hydrogen. So we expect that at very early times, this reaction will be pushed towards the right. We will have all the electrons ionized, right? So we will have a plasma. And on the other hand, when the temperature of the CMB is very small, the photons are not very energetic, and they will be not able to ionize on average, on our hydrogen atoms. So at some point, it will be more efficient for the electrons to be recombined into protons. So the equilibrium in this reaction, so if these reactions would be in equilibrium, the equilibrium would be given by the Saha equation. But I've saved you the trouble of understanding this. Let me just plot as a redshift, as a function of redshift, what we call the ionization fraction. So the fraction of electrons that are free floating in the universe as a function of redshift. When we put all the physics that we know about this problem into a computer, we see that, as we guessed, at very high redshifts, all the electrons are ionized. So the electrons are free, but as we decrease, the density is decreasing, the temperature as well, and now these photons cannot ionize the hydrogen atoms that form from time to time, and then the universe becomes essentially neutral. So all the hydrogen becomes neutral. And this happens, so this transition, when the fraction of electrons starts to decrease almost exponentially, happens at a redshift of around 1,000. Conventionally, we just take 1,100. So this epoch is super important for the evolution of the universe and for cosmology, because it's the moment where the universe passed from being full of electrons, free electrons, and electrons are very efficient at scattering light. So photon so in this universe, a photon will not go very far because it will be scattering on the electrons all the time. This means that the universe is opaque here, while as the redshift, so as the universe cools down, time evolves, the universe becomes full of hydrogen atoms, most of them, and hydrogen atoms are not very efficient at scattering visible light, scattering the light of the CMB at that epoch, which is more or less infrared. So then, very fast, you see in a few units of redshift, the universe becomes transparent to the CMB, and then the CMB photons can travel for the rest of their lives more or less unimpeded. So these photons that were more or less here in thermal equilibrium, they got released, and this is what we see today as the CMB. So we call this event, we have different names for it. All of them are not very good. We call them recombination, for instance, because electrons combined with protons into helium. But don't ask me why we call it recombination, because this is the first time that they combine. So it's not a recombination, but or in a strict sense, they were recombining all the way, So one photon recombined many million times before. So, okay, we call this recombination, or sometimes the coupling of radiation and matter, or the epoch of the CMB release, or CMB So you will hear many of these ideas. But we know that this happens at redshift 1,100 more or less, around here. So we have this, so we can structure our picture of early cosmology in this way. Matter domination, at some point, the universe becomes opaque. There's a small region in which the universe is opaque and the universe is matter dominated, but before that, the universe is radiation dominated. Very good. So let me just now go to the physics of the early universe that actually can add more evidence that we need dark matter in our universe. And also it will tell us, because more or less each piece of evidence that I'm giving you is not only for your recreational enjoyment, but also to learn something about the properties of dark matter, okay? So let's learn then a bit about the structure formation, which goes very much in line of the lecture of Kefir this morning. So one very easy question. So if the CMB that we look, so when we look at the CMB, the photons that are coming from this decoupling in all directions, essentially we see at first order homogeneous radiation, right? At 2.725 Kelvin, 725 Kelvin. So if the universe was so homogeneous at that time, so we see the isotropic, but it should have been very homogeneous. How did all the scale in the how did all the structure in the universe form? And the answer is that the answer that we have now is because of gravitational instability. From very small inhomogeneities, you can grow very large inhomogeneities just by letting gravity do its job, okay? So gravity will like to amplify a density fluctuation into something very big. So if we have some density fluctuations in the CMB, we should be able to use gravitational instability to predict more or less the universe as we see it today. So yeah, as soon as this idea came to the market, of course, the very important thing to do was to look at the CMB and to find these anisotropies, to find these temperature fluctuations, because density and temperature fluctuations are related, and they are of the same order. So people wanted to know what is the size of the density fluctuations at the CMB, right? Because from there we will be able to build or to understand the very complicated structure of the universe today. So it turned out that the first mission to measure these anisotropies was the Cosmic Background Explorer in the 90s, and then WMAP and Planck missions, they have been measuring with more and more accuracy and better angular resolution these anisotropies. But the troubling observation was that these temperature fluctuations are very small. And now you will see why this is a troubling observation. So let us, yep. So now we believe, or I don't know, we have a theory that says that they might have been created as quantum fluctuations during a period of inflation at the very, very, very early stage of the universe. But we don't know. So we know that they are there. So you know the logic of us is, okay, if they are in the CMB, then at least we can understand what happened afterwards. But so the answer would be, I think, we all believe, or many of us believe, that they were created during inflation. So let us just have a primer on gravitational instability. Gravitational instability. For that, we have to. So we will have to use some concepts. First of all, the first concept is just the concept of a density of matter, right? So we want to study the evolution of the density of matter as a function of space, right? And I'm going to assume that the density is mostly homogeneous. So the universe is very boring except for tiny ripples. Remember, Kefir was telling us before, so if the ripples of the CMB are like 20 centimeters, the depth of the well is 20 kilometers, right? So this is I'm talking about the height fluctuations or density fluctuations, super small. So I can just call my density field, so this is rho as a function of position, will be some average value which is constant, okay, rho 0. 0 here means constant in space. And then I'm defining this delta as the differential between the difference between the real density and the average value. It's not a delta function, exactly, yeah. That's a field that measures the difference from the average value. So if it's 0 in a point, this means that we have the average value. But if it's 10 to the minus 5 in one point, it means that we are on one of these lucky spots in which the temperature or the density was higher. And also we have to define a velocity field. And the assumption that I'm doing here, not yet. Let me just stop here. So the evolution of gravity is given by 3 equations that you might all know, but you don't know. The first of all is just mass conservation that tells you that the change in mass in a small volume is the mass that goes in or comes out. This is just the continuity equation, okay? You also have the Euler equation, which essentially is momentum conservation. And here I think I am assuming already that at each point of space, so the matter is moving, but only with one velocity, okay? So I'm not having a distribution of particles that is moving with different velocities. So I'm considering what is called a perfect fluid. A perfect fluid is a fluid in which all the particles in a small box, they move together, okay? So for each point, there's a velocity. And we will see that actually this is a useful concept. It's not an academic exercise. So the change of momentum comes from pressure and from gravity. Okay, this is the gravitational force because this 5 thing is the gravitational potential, and the gravitational potential is just given by the Poisson equation, right? You can still have some pressure even if you have perfect fluid. Okay. But for dark matter, I'm going to take this to be 0. So so this will be one example. But I can use this for variance with some assuming that. Well, I'll tell you later. Okay. So we can allow some pressure, and actually, I think the assumption of perfect fluid, maybe it comes also here when I define that the derivative of the pressure, this is the pressure, sorry, with respect to the energy, is just the speed of sound of my system. Okay, this is one of the things that I'm going to use to rewrite pressure in terms of density, and then I just combine very wisely these equations, and I reach an equation which is very similar to what Kefir was mentioning this morning. So the idea is that my perturbations respond to gravity. So at the end, I had to take another derivative of here. So the rate of change of the perturbations responds to gravity and responds to pressure. That's very reasonable, right? So so this is a very simple equation. It's very lovely. And actually, the most lovely aspect of it is that we can solve it. We can solve it by plane waves, which are extremely simple. So plane waves means that I just do a Fourier transform of my delta field, right? And I have a spatial wave number, and I have a frequency with which my density is going to oscillate in time. And this frequency is given by the difference between the effects of pressure and the effects of gravity. So, and you see something very interesting here. So short wavelength perturbations, the ones that have so the wavelength is the wavelength is very short. So this means that the wave number is huge, right? It's the inverse of the wavelength. So this term dominates over gravity, and then this frequency is just real, and the solution is going to oscillate in time. So this means that there's a critical for very short wavelength perturbations. So we are talking about waves of this size. The pressure. So gravity tries to pull regions which are overdensed together, but the pressure pushes the matter outside, okay? So pressure is stronger than gravity. So gravity tries to compress, but pressure always wins at short wavelengths. However, when we go to long wavelength perturbations, above this critical wave number, what we call the Jeans wave number, actually, this this thing you can neglect, and then we get the square root of a negative quantity that is an imaginary number that multiplied by I is a real number, and you get exponentially growing solutions. So this means that in this regime, for very long wavelengths, so if a perturbation is very long, it can actually grow. So in a sense, pressure is not sufficient to control the growth of these very large perturbations, or the speed of sound is not fast enough to propagate the pressure waves and expand this. So gravity wins on the long scale. And actually, this instability is an exponential instability, okay? So you have exponential growth of density perturbations. Very nice. When I talked about a critical wave number, the one for which omega would be 0, this can be rewritten in a length, which is the inverse of the wave number divided by 2 pi. And this is the so-called Jeans length that separates these two regimes. And note, very importantly, that this depends on the speed of sound, okay? So the speed of sound is essentially how do you change the pressure when you change the energy. And imagine that you have a gas of particles that has no pressure, so the velocity of these particles is very small. They are like super quiet, non-relativistic particles. Then the speed of sound is going to be 0 because this gas has no pressure, essentially, okay? So for non-relativistic particles, there is no compensating force, and all the perturbations want to grow, right? However, if you have a gas of photons and baryons, so at the very early universe, I told you that electrons are interacting with photons very efficiently, right? So in the radiation domination era, before photon decoupling, electrons, photons, and baryons are all very tightly coupled. And instead of thinking about a fluid of photons and a fluid of baryons, it's convenient to think about a fluid of photons and baryons together. And then this fluid, on average, it moves like an ideal fluid to some approximation. Okay, it moves together. So if you have an overdensity of photons, it's because you have an overdensity of baryon density. So the fluid moves together. Good. And but however, for this fluid, the velocity of sound, if you want, is actually the velocity of light, because perturbations can travel mediated by the photons. So the velocity of sound is very fast. Sound waves in a relativistic fluid can be very fast, because okay. So this is going to be the difference between baryons and dark matter. However, there's another difference in this derivation. I didn't tell you. So I didn't talk about expansion of the universe, okay? And I didn't talk about general relativity. So here what I'm doing is just, so I'm just saving you the details, but I just give you the right equation, or the similar equation to the equation that we found now, when I include the effects of the expansion of the universe. This is going to be important. I'm not doing anything about general relativity, so this formula has some limit of validity, but it's okay for us at the moment. So the change between the previous equation and the equation in an expanding universe, so gravitational instability in an expanding universe. So now my average density is decreasing also. As the universe expands, my density of matter is decreasing. This is what is changing. So because of the expansion of the universe, we have an extra term here, which is essentially, if you think that this is a wave equation, this actually is a friction term. So it behaves like friction, okay? If this would be some harmonic oscillator, this would be a friction in the harmonic oscillator. And then something comes up here, which is that the wave number I have written, it comes divided by the scale factor, because this is now not a physical wave number. I decided to change the notation to complicate your life, and this is now a comoving wave number, okay? It's a comoving wave number. The one that doesn't change when the universe expands. Actually, I complicated your life to simplify it, because then a wave in comoving coordinates will always have the same wavelength. That's nice, right? That's reassuring. Very good. So these are the two changes, and this equation is a bit more complicated than the previous one, but still we can get essentially the physics, the physics solutions, because we have already learned them from the previous example. First, what I'm going to do essentially is just to do I already used a Fourier transform for space. So this is the equation actually for the one Fourier component, and this Fourier component is defined like this. X is now comoving coordinate. Sorry, this is physical coordinate. So what's the effect of the expansion? There are three relevant cases. Very short wavelength perturbations, remember, are the ones in which this term is more important, and so they are oscillating, okay? So gravity you can neglect, so then you have oscillations. However, because of the friction, you will have now damped oscillations. So the oscillations will tend to decrease. So you have a perturbation which is really small size. The universe is expanding, and the perturbation is going to oscillate around 0 with decreasing amplitude. It's going to be lost. But what happens with long wavelength perturbations? Remember that those are the ones that grow exponentially in a non-expanding universe, are the ones that can amplify perturbations to create structures of order 1 like we have today. So it turns out that this depends on how the universe is expanding, okay? So it depends on this Hubble constant. This Hubble constant, remember, is proportional. Well, so the Hubble constant square is proportional to the density of the universe. So in radiation domination, this density is increasing, so it's decreasing very fast. But in matter domination, it's decreasing slightly, or not so fast, okay? In radiation domination, this is decreasing as 1 over the scale factor to the 4. In matter domination, it's decreasing as 1 over the scale factor to the 3. So then it's reasonable that this solution depends on whether we are in radiation domination or matter domination. So in radiation domination, we can think that our fluid, our matter component, let's think that this is a dark matter component that is completely decoupled, but is in a universe which is dominated by radiation, okay? So then the gravitational potential is dominated by radiation, is much larger than gravity for itself, and we have dark matter. Let me just say that dark matter doesn't have, so it is really made of non-relativistic particles. This equation, sorry, the speed of sound is 0. So for this kind of completely decoupled matter, we have this very simple equation, this very simple simplification, and this equation has two solutions. One is constant, and the other only increases logarithmically. So from an exponential growth, we have managed to get a solution that typically increases logarithmically at most. So this would be the solution for the dark matter in a radiation-dominated universe, okay? But what happens when the dark matter enters into matter domination, when it's himself the responsible of the expansion of the universe, or the Hubble parameter? Now, this coefficient changes, so the Hubble expansion rate changes. Actually, you can derive these two coefficients if you have time. And so I'm mostly caring about long wavelength perturbations, right? So this, let me just neglect this now. So the unstable modes. And now, the average density is a function of the Hubble constant, and the Hubble constant is a function of time. So I can rewrite this thing as a power of time, and I can solve this equation, and this equation has a growing mode. Okay, it has a decaying mode, but also has a growing mode. But has a growing mode that actually only grows as the scale factor. So that's the important thing to take from here. You can do these exercises when you have time. The important thing is that now, when matter perturbations in a matter-dominated universe can grow with time, or will grow with time due to their own gravitational interactions. Okay, so if I just, yeah, you got it. So now let us see why do we need dark matter. So here in this picture, I'm showing you the evolution of a fluctuation. So now let us think that I'm in the very early universe, in a very flat universe, very homogeneous, and here I have a density. So I put a slightly more amount of baryons or photons and dark matter, all at the same time, but only a tiny amount, a very small amount in this place. Let's see what happens. So essentially, general relativity tells us that I cannot use my equations at very early times, so I have to start around here. I think Javier will confirm and will tell you why do I have to start here. But okay, this is good enough for me. What happens with the baryons? The baryons are very strongly coupled to the photons, right? And remember what we found? The baryons and photons, they have a very large speed of sound, right? So they typically, at least in this example, they are going to oscillate. They are going to oscillate in the radiation area, and they are going to oscillate in the matter area. They don't care. And you see, they are oscillating, and they have damped oscillations as well. So this is what happens with baryons. But, of course, when the CMB is released, now photons and baryons, they are not coupled anymore. So photons can travel freely, right? And photons can travel freely, they travel, and then baryons are left alone. And now they are a matter perturbation in a matter-dominated universe. So they can finally grow, and they are going to grow with the scale factor. So in this log plot, they will go with a straight line. So if no dark matter, my perturbation in baryons will only grow from a very small value, okay? Which is similar, as you see, is similar to the original number of the perturbation. So now let's make the calculation. We have a temperature fluctuation of the order of 10 to the minus 5. This means density fluctuations of order 10 to the minus 5. The CMB decouples at redshift 1000. So from redshift 1000 until today, the scale factor has changed a factor of 1000, okay? So what is the size of this perturbation today? 10 to the minus 2, right? Very roughly. So from 10 to the minus 5, I can only increase the density contrast of my perturbation until 10 to the minus 2. So this means that my perturbation of order 10 to the minus 5 at CMB is now a perturbation of 10 to the minus 2. But we don't observe, the universe is not an homogeneous universe made of perturbations of order 10 to the minus 2, right? Here we have a galaxy, and here we have an empty space, right? So we really have to reach delta equals 1. So we really have to have, we have to break the linear growth and go to nonlinear growth. We have to reach delta of order 1. And this is only thanks to the dark matter. Why? Because dark matter is not tightly coupled to baryons. Okay, let me just assume. What happens if the dark matter doesn't know anything about baryons? I start with a perturbation which is essentially the same than my baryon, and then in a radiation-dominated universe, I told you that this perturbation can already start to grow more or less at a logarithmic rate. Okay, that's not very much. That's why this growth is quite a boring growth. But when the universe becomes matter-dominated, then it can start to grow. It is not subject to photons, so it can continue to grow. It was already growing, and now it can continue to grow. So then when baryons are finally released from the CMB, they don't have to grow all the way to order 1 perturbation. They can actually fall in the potential well of the dark matter that was there. So now, coming back to my position, what happens is that while baryons are oscillating inside of my gravitational potential, dark matter is getting compressed. Dark matter is getting compressed, and the baryons cannot compress with it because they are coupled with photons, so they continue to oscillate, but the dark matter continues to compress. So when finally baryons are devoided with photons free stream away, now the baryons can catch up, can go very fast to the depth of the potential well of cold dark matter. Okay, they can fall into the gravitational potential of the dark matter, which is now more dense, and they can save the day. They can make density perturbations today of order 1, and they can explain why our universe is so much fun instead of a boring universe with density fluctuations of 10 to the minus 12. And you see, from here we have already learned something. We have learned that dark matter has to be somehow weakly coupled to baryons. Otherwise, this would not work. If it's very strongly coupled to baryons or to photons, right, it would behave like baryons. It would oscillate. So the speed of sound of the baryon fluid, of the dark matter fluid, has to be small. Very good.
But this is essentially it's because the curvature of space-time is that makes the potential waves that the ordinary matter or the galactic matter fall in. So it is the main reason is the curvature, not the dark matter, the existence of dark matter. So we may take dark matter and talk about curvature.
You're saying that the main effect of dark matter here is providing a large curvature, a large potential well for
Yes.
yeah.
We can talk about curvature instead, not about dark matter.
Yeah. So here the important thing, but okay, here the important thing is that there is some substance that can that you see at the epoch of the CMB can have a more or less, should be able to have a more or less large density or large curvature fluctuation. Should be able to explain you why the curvature is larger than the ones that we see in the CMB, in a sense, right? Because in CMB we're seeing temperature fluctuations. But yeah, if you have a mechanism that gives you the same potential wells, this could explain this phenomenon. Yeah. So exactly, I'm very happy. I mean, you have to try to get the essence of these things, because we might be completely fooled by the fact that we really think that dark matter should be made of particles. But what I'm trying to tell you in these lectures, at least so far, is that so I want you to understand the effects, the physical effects that lead us to think that there is some dark matter. Okay, and here the physical effect is that we have some potential. So we have something that increases the potential well before baryons can compress, okay? And therefore, it's very easy for baryons to then go into these potential wells afterwards. But if you have any mechanism that does the same, it could explain this. And also, it could explain something else that is one of the most striking and important indications of, or one of the most important tools we have in cosmology, which is the anisotropies of the CMB spectrum. I just wanted to make the connection between what I have explained you and what we see in the universe, what we see in the universe, okay? So now I'm reverting the picture. So time and scale factor grow in this direction instead of that direction. And I'm giving you the same picture again. So we have you see, at more or less a redshift of 3,000, we have the transition between matter-dominated universe and radiation-dominated universe. And at a redshift of 1,000, we have the release of the CMB. So here's the universe is transparent, more or less, and here the universe is opaque. And here I plot you the typical trajectory of a photon. A photon before the recombination is a very busy object. It's always scattering on electrons, okay? But then, as you see, the mean free path increases, and at some point, it has its last interaction more or less around this time, and then it travels in a straight line towards us. Also, we call this moment, or this surface, the last scattering surface. So the recombination and blah, 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 all this, another name for you, the last scattering surface. And of course, it's not a surface, it has some thickness. Good. So this was the picture that I drew before. Now we can see what happens with our density fluctuations, right? So during radiation domination, I don't know if you see it, but here we have a dark matter fluctuation. So the universe is more or less homogeneous, but I have put some more matter, some more dark matter here. And this dark matter is slowly increasing its contrast. So it's growing a little bit, it's compressing a bit. And here I represent compression by making it more black, and also by compressing it physically. You see that in this case, we only have the logarithmic growth. That's why here it doesn't change very much, but only if you have good eyes, you can see that it's growing. But then when the universe becomes matter-dominated, then this guy can go linearly, can compress linearly. And this is what it's doing, okay? And it will arrive to the moment of to the last scattering surface with some density. So it arrives, of course, more dense. So dark matter is more dense at last scattering surface than at radiation domination, at the matter radiation transition. So what happens now with baryons? Baryons are accompanied with photons, so they are now these yellow blobs, and you have seen before, they are oscillating. So they are oscillating, they are compressing, and then here the pressure is so high that the density decreases, and then increases again here. So you have these density oscillations. Okay, so some of these overdensities, okay, will lead to situations like this in which the baryons are last scattered when they are in a point. They are not compressed, but they are just expanding, right? So we'll have yeah, exactly. So you have compression, rarefaction, compression, rarefaction. So some of these waves will arrive to the moment of decoupling compressed, and some others they will arrive with an under density, right? And depending on the moment, so because the period of these oscillations is going to depend on k, right? Which is so the wave number. As a function of wave number, we will have compression or rarefaction at the epoch of last scattering. I'm showing you another example. For instance, this wavelength is longer, the wave number is smaller, and the frequency of the oscillations is slower. So then this, and the wavelength is longer, right? So there is, for instance, this wave, it started to grow seriously here, and then it arrives, so the maximum compression of the baryons happens also at the maximum compression, of course, of the dark matter, but it happens in the first compression, okay? Now, if you have a wavelength that is smaller, therefore the oscillations are faster, and typically you will have another, so you will have another rarefaction before. But there is this characteristic wave, and this is the wave, the biggest wave that can show a compression, okay? And also you have another interesting effect. So for very small length scales, the oscillations are so fast that you can have compressions and rarefactions inside of the last scattering surface. So in a sense, you are going to see photons from here, and you are going to average out, okay? So you will see some blurring. So you will not see underdense or overdense. So actually, when we look at the sky, we see these temperature anisotropies, and when we do an analysis, so when we do an analysis of harmonic, the spherical harmonics, so we analyze essentially the power at each of these spherical harmonics, we see precisely these oscillations, okay? We see precisely that there is a first peak, okay, where a huge amount of temperature that corresponds to the size of this particularly sized perturbation that arrived to the surface of last scattering at the farthest compression, at the biggest compression, okay? So this particular length scale here has to correspond to this first acoustic peak. But also we say that so if we go to smaller angular scales, this means smaller length scales, right? Smaller waves. Smaller waves, they have more oscillations before reaching the last scattering surface. And actually you have, for instance, here another peak. That's a peak in which baryons made one, so they compressed once, and then they got, so let's go to the third peak first. They compressed once, they expanded, and they compressed another time. And then the photons were released. So this is called the second compression. And here there's this funny peak in the middle that is a peak, but it corresponds to a rarefaction. And why is this? Because here, this is like a Fourier spectrum. And this is like a Fourier spectrum of the density fluctuation. So you have a density, and you have a positive density fluctuation, this is more density. And this will show in the spectrum like a peak, right, at a given scale. But if you also, if you have a rarefaction, so if the density is smaller than 0, this will also appear in a power spectrum, because the power spectrum is the amplitude of your fluctuations squared, and then the sign doesn't matter. So both compressions and rarefactions, they show as peaks. So maximum compression and maximum rarefaction appears as peaks. However, the amount of matter and the amount of baryons are going to affect differently these peaks, okay? Compression and rarefaction peaks. And this is what you see here. So this is a simulation of these anisotropies as a function of the amount of baryons, for instance, right? So you see, when you increase baryons, the temperature, and this is of course, this is the temperature fluctuation averaged over, so you take all the modes that have a particular scale, and you make an average, okay? So a lot of power means that you have a lot of fluctuations in that particular scale. And also here you see, finally you see that at very small scales, you start to see the effect that you're averaging out many oscillations inside the last scattering surface, and you see other effects. But the main important things are these acoustic peaks for what I wanted to say, because we understand these acoustic oscillations very good, so we can make predictions like this, and we can study, for instance, the dependence with the baryon density, but also with the total matter density. But you see particularly what happens, and it's very clear in this picture, right? So if you increase the baryon density, the compression peaks are stronger. So you have more temperature fluctuations in the compression peaks. Why is this so? Because you increase the amount of baryons, of course, so they are able to compress the plasma more, right? So remember, what is the physics of this first compression peak? You have a bit more baryons here than the rest of the universe, and then they compress. And when they are most compressed, the universe becomes transparent, and you see that the universe was more compressed. We see a higher temperature here. However, in the rarefaction peak, you put these baryons, the same amount, but at a slightly smaller scale, so that they compress once, and then they are expanding. Then you take the picture. You release the photons. Okay, and the compression depends very much on the mass of the baryons, but the rarefaction does not. It depends more on the speed of sound and on the pressure, right? So what you see is that the first and third peak, which are the compressions, the pictures when the baryons are most compressed, they increase because we are putting more baryons to compress them. But the rarefaction peak actually decreases, or well, it doesn't increase definitely, right? As you see from this line is increasing the baryon density. So from this line, you first increases a bit and then decreases. So it's just, you have a much less clear behavior. Of course, it has to depend a bit on the baryons. But the important thing is that it has a completely different behavior, this than this. So just by analyzing the ratio of these two peaks, we can get the baryon density, for instance. But actually, what we do is, of course, we run a lot of models with the CMB and try to measure the dependence of these anisotropies with all the parameters, the cosmological constant, the baryon density, the total matter density, the Hubble constant, everything. And we can get super precise results, of course, because these anisotropies are measured with amazing precision. And the result is, again, that it confirms what I was telling you before, but in a much more precise way, that the universe it looks like it is having this 70% of cosmological constant, this 25% of dark matter, or whatever we want to, whatever we want to name the thing that has these gravitational effects, and this 5% of 4.4 of baryons. Okay, so this is a confirmation, but of course the error bars are so small that you can also start to see that not all the data sets are perfectly compatible. So I invite you to get lost in the literature and look for interesting things that can explain this difference and discrepancies. But what concerns me here the most is that the big picture is served. So the main meal is served, and the main meal is the cosmic pie with 70% dark energy and 25% unidentified dark matter. So now let us just jump and let's make one assumption. So I hope I've convinced you that we have a good set of environments where we think we need some physics beyond the standard model, physics beyond variance. So now I'm assuming, because this is a particle physics school, I'm assuming that this dark matter is made of particles. But of course, one has to explore any other possibility. So we have this beautiful theory of particle physics, the standard model of particle physics, and we have plenty of particles. So can any of these particles do the job? Okay, we can see. So first of all, we have many particles that are unstable. So these particles, they will not last as long as today, so forget about them. So these are most of the heavy quarks, the gauge bosons, the Higgs boson, and the heavy leptons, the tau and the muon. Now we have baryonic, so we have particles that we have already associated with baryons, and we know that dark matter is not made of baryons, okay? Okay, some people think that dark matter might still be made of baryons in a very funny way. So just remember this, because it's a very funny, interesting possibility, but I'm not going to discuss it at all. But the baryons are made of up quarks and also a bit of down. But if the down is together with the up, it likes to be stable and made of gluons. These are baryons, and this cannot be my dark matter. Now we are left with the electron, but the electron is charged, so actually cannot be dark. So we would see electrons so nicely. And if you can say the same about positrons. We would see also positrons very easily, and they don't have the right characteristics at all. So they interact with light. They radiate very efficiently, so they would clump. They would be a disaster candidate for dark matter. And we have the photon, which cannot be dark matter because it's a relativistic particle. It has no mass. So we're actually left with the neutrinos, right? So in principle, the neutrinos would be ideal dark matter candidates. They have mass. They are very weakly interacting. So this is what people thought immediately. So neutrinos are the standard model dark matter candidate. But what is the problem with neutrinos? And here comes another lesson, the last lesson about dark matter that I have not told you yet. So let me show you why neutrinos cannot be the dark matter. There are several reasons, but and I think you have already heard one. But I'm going to tell you another one. And the reason is that neutrinos are produced hot in the early universe, and they free stream. So neutrinos are not a very good, perfect fluid, because if you put a small box, actually you have neutrinos that go in all directions. So the neutrino velocity cannot be taken to be zero as dark matter. And I'm going to show you this, right? So neutrinos are thermally produced in the very, very early universe at temperatures of the order of 1 mega electron volt, when the redshift is 10 to the 8 or something like this. The interactions with the standard model are not very efficient to keeping them in contact, and they just, from that moment on, they just simply free stream. They just move along their inertia. So you're using their inertia. So the question that I want to ask is, so okay, a neutrino that was produced in one particular point, at which point will it be at the epoch of the CMB? So what is the distance? What is the comoving distance that a neutrino has traveled? Okay? That's a very well-posed question. So if I have my comoving coordinates, right, I just want to know how far the neutrinos moved since the beginning of the universe. And we studied, so we heard this already in Kefir's talks. So the comoving distance is essentially that you travel, so that any particle, that a photon, the comoving distance that a photon would travel as a function of time is related with the differential of time and the scale factor, right? You remember that? Now, if a particle, but neutrinos are not relativistic all the time. They have a mass, right? So they will have a velocity, so then you will have to multiply. So the distance that they have traveled is just the distance that a photon would travel multiplied by the velocity. And the velocity is just, well, I have it written there, so why do I? So this is essentially this formula here. So we want to know what is the integral, so what is the distance traveled from 0 to the CMB time. And we can write the integral over time in an integral over redshift, because we know how the universe expands as a function of redshift in these lectures. And this delta T over R becomes delta C over the Hubble constant. You see how important it is to know the Hubble constant as a function of redshift. And this is the velocity of a neutrino. The velocity of a neutrino is the momentum divided by the energy. The energy is the momentum squared, so it's this combination, the relativistic combination. And the only problem, or the only thing that we have to take into account here is that as the universe expands, the momentum of light decreases, right? So the wavelength increases, the momentum decreases, and the same happens with any other particle that is just moving around. So the neutrino momentum experiences some redshift. And neutrinos were produced thermally, so they have typical momenta. When they are produced, they have typical momenta of the order of the photon, of the photons. So I'm going to parameterize the momentum as the temperature of photons, which is a typical momentum for the photons. And of course, I have to put the redshift, right? Because the momentum increases at early times, decreases at late times. And then just this X parameter, it tells me how small or large my momentum is compared with the photon, with a typical photon momentum. So, okay, yeah, we have also to note that at very high redshift, the neutrinos with this expression, right? So the momentum will be much larger than the mass. So the neutrinos at very high redshift are relativistic, and as the momentum becomes of the order of the mass, they will become non-relativistic. So this is what is going to happen. So we have to do this integral, and so this delta C divided by Z in this interval, the time from 0 to the CMB, and the velocity is first 1, but then it becomes suppressed by this factor, which is the momentum divided by the mass, okay? And this transition of, so when the neutrinos become non-relativistic is when the momentum is similar to the mass, is when this thing is of order 1, right? This is the momentum, and this is the mass. So when this thing is of order 1, this means that at redshift, that I call redshift of non-relativistic, this is the mass divided by this X parameter and the temperature. So at that time, so this is the redshift that changes the regime from relativistic to non-relativistic. So now let's compute this integral. So first of all, what I'm going to do is very easy. So the Hubble constant, I can just, I'm going to, so I want to study the propagation of neutrinos before the CMB release, so more or less the universe is radiation dominated, okay? No, you know that not exactly. There's a small period of matter domination, but I'm going to neglect this. Let me just say the universe is radiation dominated, so I can use my expression for the Hubble expansion rate as a function of the radiation density only, and I get this very simple expression. And I already realized that the units of my length are going to be these units, right? So inverse of Hubble again, but enhanced by this factor. Remember that omega 0 of gamma is 10 to the minus 5 or so. It's very small. Good. So I have to do this integral, and now from CMB to infinity, and the velocity is, I can split this integral between the redshift of the CMB and the redshift at which neutrinos become non-relativistic, and from when they become non-relativistic until infinity. So the early times and late times, and I get these two expressions. This is very simple because velocity is 1 at very early times, so this is the integral of 1 over z squared. So I get this with a factor of 2 that I, with a factor of 2 of 1/2 that I forgot, sorry. And when the velocity is, so when the neutrinos are non-relativistic, they get this expression. and then they get an additional suppression of 1 over c in the numerator. So I get 1 over c, and the integral is a log. It's a logarithmic expression. But now if you follow me, so this redshift of, it has to be very large, so these ones are completely irrelevant. So the redshift, 1 over the redshift is essentially the same factor. So at the end, this integral is just, if you allow me to take the log of order 1, is just the prefactor, and then 1 divided by its redshift of non-relativistic. And this is essentially this factor that we wrote there. So that's the calculation of the neutrino free streaming length. And now we have the neutrino free streaming length as a function of the neutrino mass and as a function of this parameter. So if I write this in terms of numbers, that physical distances, we see that if the neutrinos would have 1 electron volt energy, they would have traveled something like 100 megaparsec. And this only at the epoch of the CMB. And I have neglected the log in this estimate. And I've neglected the factor of 2. So 100 megaparsec, that's the scale. So that's the scale of the largest clusters that we see in the universe. And definitely, if neutrinos can travel this distance at the epoch of the CMB, so the neutrinos that were originally in some dense region will just free stream, and then they will fill other under dense regions, right? So if neutrinos are allowed to travel that far, they will wipe out any density fluctuation that we might have. So neutrino free streaming is very bad. It wipes out density fluctuations on scales smaller than the free streaming length. So we cannot allow dark matter, definitely not neutrinos, to if neutrinos are all the dark matter, yeah. We cannot allow our dark matter candidate to free stream very long. Okay? So, but you can breathe because, yeah, you know, neutrinos are not the dark matter of the universe. First of all, this formula is not valid down to any mass. You can just check that. And second of all, neutrinos, we know that with these very small masses, neutrinos cannot be the dominant component of the dark matter of the universe. So we can allow that a subdominant component of the dark matter free streams. That's okay. And actually, we can somehow, we can even constrain the amount of dark matter that we can have in free streaming particles. But all of it, it cannot. So you cannot allow all the dark matter to be free streaming over long distances. You remember probably from the lectures of Silvio Pascoli that the relic density of neutrinos, of neutrino dark matter, so if I take all the neutrinos that are produced in the early universe and I allow, so they convert them into so they free stream and they convert into non-relativistic particles, so they behave as matter. So the amount of, so the contribution to dark matter would be something like the sum of the neutrino masses divided by 46 electron volts. So of course, if the mass is of the order of 1 electron volt, this is very small. It's still a small number. So it's not at 25%. So neutrinos cannot be the full amount of dark matter, and then we are safe. But we have learned the lesson. Oh. Ladies first. Hmm? This one? Yeah.
So if I'm not very sure, probably I just want to clarify that in that case, that lambda free stream against the suppression of the high mass of the sterile neutrino, and in that way the lambda is suppressed, and that's why it would be the dark matter.
Yeah, exactly. Oh, sorry. Yeah, exactly. So then this is the lesson to be learned is that, of course, if I make another particle, sterile neutrino, you can say it is similar to a neutrino. It has a similar abundance, and it has similar temperatures. What I've assumed here, well, actually, I have not assumed anything here. But exactly, but if you say sterile neutrinos are the dark matter, and you have to allow this mass to be of order kilo electron volt, so that this scale is safely below. But I will comment a bit more on that. Give me 1 second. We have. What is X? Oh, X is a parameter that is going to be useful later. So I've parameterized the momentum of my neutrino, and this calculation is going to serve you for any free streaming particle. But I have to tell you what is the momentum of a neutrino as a function of redshift to make this integral. So I have decided to parameterize it in the following way. Like the momentum that a photon would have. The momentum of a photon nowadays is related to the temperature, right? Okay? So that's why I wrote T0. But as we redshift, as we go back in time, the momentum increases, right?
So x T0, 1 plus z is equal to momentum.
Exactly. Yeah, sorry. I should have written P equals. Very sorry.
Then X is free forever, right?
X is a free parameter, exactly. X, yeah, that's very good, exactly. X is something that if the neutrino has, if the particle that is free streaming has a similar momentum to the photon, it's of order 1 and nothing changes. But of course, if X is very small, right? So if I create a particle that is much smaller momentum than a photon, then all the things that I'm telling you will be changed. That's why also I kept this X here. So if I sense, and this is going to be one of the motivations. So this is why we can have very light dark matter candidates if you produce them with very, very, very small momentum. Okay. But this comes later. You are really fast. So here you have a simulation of large-scale structure formation in which I have cold dark matter. This means very small free streaming scale. And here I have neutrino dark matter. And you see that the pictures are very different. So here you see that neutrinos have traveled some distance in this plot, and actually the structures are very smooth. Okay, so the dark matter distribution here is very smooth because neutrinos have spread it a little. But in the case of completely cold dark matter, this means no free streaming at all. You see that there is plenty of substructure. Okay, and it looks like so what we observe in the universe looks more like this picture than this. But of course, one has to be quantitative about this. Okay. So let's try to be quantitative in a qualitative way. So the way we are quantitative in a qualitative way is just by making analysis of the plots that Kefir was showing this morning and yesterday. This distribution of galaxies. Okay, so distribution of matter in the universe, which is, of course, correlated with the fluctuations that we see in the CMB. So what you see here is the typical fluctuation in the temperature of the CMB and in the matter distribution in the universe. Okay, so here you have the matter distribution at huge scales, right? So megaparsec. So these are tens and hundreds of megaparsecs. No, I don't know why they had this idea of writing everything in terms of K. But this is the amount of fluctuations in the distribution of galaxies at very large scales. Good. And here you see, so these are typical predictions, and here you have the observations. And the distribution of matter can be measured by the cosmic microwave background, of course, but also just by counting galaxies. There's one point from clusters of galaxies, but also we can do weak lensing of the universe and study the distribution of gas clouds at very high redshift. This is not very important. The important thing for you to know is that we can more or less measure what is the size of the fluctuation in the matter in the universe. So we know more or less how wavy the universe is at very large scales with some uncertainties. So we can be quantitative about it. And for instance, we can just, in the case of neutrinos, we can compare observations that you have here. Okay, this is just a subset of these observations with the predictions for neutrino dark matter, of a dark matter component that is free streaming. And you can see what happens, that the power at small scales, so large wave number means small scales, okay? You don't have to care very much about the numbers, but you have to really understand that this is how important fluctuations are at a given scale as a function of the scale. And this, for neutrino dark matter with some mass, the small scale fluctuations are damped. And this is because you start with some dark matter at these small scales, but then the dark matter goes away. So you lose this fluctuation. Okay, fluctuations dissipate away. So this is what happens, and we can put constraints, of course, to the mass of the neutrino and to the mass of any hot dark matter candidate. So, So the lesson to be learned from here. The dominant component of dark matter must be cold. But by cold, we mean precisely what I've told you before, that the velocity is very small. The velocity at the epoch where it's important for structure formation. I just made the calculation at the epoch of the CMB, because so this will be valid for the CMB anisotropies. And actually, you can prove as an exercise that a non-relativistic particle doesn't go very far after matter radiation equality. Okay, so the rest of the calculation until today is not that important, but you can just do it, or you can just very easily understand why. And also, I just wanted to write you here. So for the calculation I've done, the dark matter particles that reached 0.1 comoving megaparsec at the epoch of the CMB, so the particles, the neutrinos that reached 1.1 megaparsec, they had a velocity at the epoch of the CMB of the order of 10 to the minus 3. So they were really non-relativistic. The velocity was 3 orders of magnitude smaller than the velocity of photons. Okay? So if the velocity of your dark matter at the epoch of the CMB starts to be larger than this 10 to the minus 3, you will have something like hot dark matter. Okay? You will have dark matter that doesn't do what is required to do. It has to also create structures at very small scales. Well, not very small, but relatively small scales. Dark matter is not only producing the large clusters of galaxies, it's not only providing the gravitational potentials where baryons can fall and form large clusters of galaxies, but also, large clusters of galaxies, also clusters of galaxies and also galaxies, although the galaxy part is more tricky. So, and then just wrapping up, you came with these very nice comments. If we have a thermal relic, this means that thermal relics are typically created with momenta. Yeah?
Is it formula? Is it a condition or is it a taking the log minus part of certain mass? Is that formula a condition or is it working?
I'm not sure if I get this. This formula? Yeah. This is the formula that I just computed. This is the free streaming length.
But for larger one, for more mass.
Well, I can put the mass that I want. Because, I mean, you have to, exactly. Sorry. I decided to write it like keV, because if I write it like electron volt, this was 100 megaparsec. But if I write it now as 1 keV, you see that this is starting to have the size of a galaxy. And then at the size of a galaxy, you can always, I mean, is where we start to lose our information or detailed data about structure formation. So more or less, if a particle has more mass than kiloelectron volt, we will start to mess up with scales which are already controversial.
What happened with warm
dark matter? Exactly, very, very good question. Warm dark matter is precisely the type of dark matter that is not cold, not hot. It's precisely on free streaming scales of this type. So maybe even a bit shorter, I don't know. So the idea is that if you free stream just the exact amount, then you can erase you can erase, or you can decrease the power at some particular scales, which corresponds to small galaxies of the small galaxies of the center of some galactic clusters and so on. And you can you can diminish the abundance of this cluster. So only the ones that were very dense will survive, right? Because the underdense will just so the very dense ones, even if they free stream something, they can come back. But the super underdense ones, they will not survive. So you can lower the amount of halos of dark matter of a typical size. And actually, for some time, it was believed that this was precisely the case in the universe. When we look around the Milky Way, we didn't see many small galaxy satellites, if you want, or mini halos, right? So it was very interesting to consider warm dark matter, because with warm dark matter, you can start to diminish the probability of these halos to exist. So yeah, warm dark matter would be this in between hot and cold, and could be interesting. The problem is that this warm dark matter kicks in a regime where baryonic feedback is very important. So it's very difficult to conclude that actually the dark matter has to be warm, or that we don't know how to implement baryonic feedback in our n-body simulations, or our n-body simulations are completely wrong. So the warm dark matter is super exciting, but it's really, you have to be a real expert in structure formation to follow, I don't know, to give some advice about it.
Yeah, a question about X. You said it's a free parameter.
Yeah.
So if you're going to say that this equation is more or less the same for cold dark matter and warm dark matter, how are you fixing X? Or what are your other?
No, X is the parameter that you have to put to extract some conclusion. So let's say you want to extract some conclusion on neutrino, on standard model neutrinos. Then you know that their momentum is very similar to the photons. So you put X to be 1, or 0.5, or 0.3, or you can do even an average. Now imagine that you want to have a decaying, so you have a decaying dark matter. Sorry, you have some dark matter that was produced by the decays of some particle, and therefore is much hotter than photons. It can be, that has more momentum. Of course, it has a very large mass, but it can be hotter than photons in a sense. In the sense only that their momentum is larger than the momentum of photons. Then you have to take X to be larger than 1. And you will have to compute how much. But imagine that you're interested in axions. Then axions are produced, some of them are produced thermally, and you will have to put 1. And some of them are produced non-thermally, and you will have to I will have to give you the typical momentum of axions produced non-thermally, which is something like 10 to the minus 20, and then you will see that you will never care about this. But you see, in order to use this formula, you have to come and give me the value of X.
It's fixed once you figure out what you want, it's fixed.
Exactly. Once you fix the model, you give X, and then this formula tells you how far the dark matter traveled at the epoch of the CMB. But exactly, that's very important. So if the momentum is equal to the temperature, so the thermally produced particles, typically they have this relation, they must have large masses, at least KB or more, okay? So this is what we learned. And the low dark matter candidates are only possible if they are produced non-thermally. So we learned these two things from this example, okay? So, yeah. Exactly. So we have learned something more about more or less the nature of dark matter. This is a picture that you already saw. And now that we have excluded neutrinos, we are left with the conclusion that if we want to have particle dark matter, we have to look for something beyond the standard model. And I'm going at half the speed I should. This was the second lecture. So we have to go and look beyond the standard model. So this is a summary of the first lecture. The first lecture is that cosmology seems to demand a new particle, right? To fill the concept of dark matter. But But particle physics actually is very happy to call or to answer that claim, because in particle physics we have this beautiful standard model of particles. So we have a particle content that explains all the particles we have ever observed in colliders. We also have a Lagrangian model for the dynamics, for the interactions of these particles. But actually, more than particles and dynamics, we have many questions. We don't like this model so much, at least theorists. Experimentalists are very happy. Well, maybe not. What about including quantum gravity in the framework of dynamics? Or why the parameters that rule these Yukawa couplings and the gauge couplings, why do they have these values? Why this model is based on this gauge symmetry, which is why we have these particles. Why 3 generations? Why 3 copies of fermions? Yeah, there are many questions. Also, there's one question, the strong CP problem. Why QCD does not violate CP or parity and time reversal? So luckily, we have theorists, and theorists have plenty of ideas to answer these questions. We have string models, granulified models, have axions, supersymmetric theories, and we have this very strong feeling that in nature there should be more symmetry, there should be more fields, and there should be more particles. And but apparently John Ellis doesn't like he doesn't believe in the strong CP problem. He was wearing this shirt. I think that the ICTP T-shirt includes the theta term, right? So you are in an axion sensible community. Very good. So particle dark matter. So how do we play this game? How do we play this game for 1 minute? This is just what is going to come tomorrow, just for you to go to bed, to go to a warm bed. So we have to find. So the main motivation or the main framework here is that in the minds of theories we have many ideas of new particles that have to exist beyond the standard model, and very interestingly, some of these new particles that we can guess actually they are good dark matter candidates. So therefore, I think it's very interesting to explore the possibility that some of the particles that are motivated by particle physics can be the dark matter of the universe. The characteristics that this dark matter particle has to satisfy, we already know. It has to be stable, has to be weakly interacting with light, blah, blah, blah. It has to be produced in the right amount, and so on. So now you know these things very well. And well, I will try to explain a little bit our favorite candidates, and I will try to explain a little bit one of the most interesting questions that we can ask from the phenomenological point of view is how we marry our theoretical ideas with the idea of dark matter, and we put some extra constraint into our models. The first constraint that we are going to have for dark matter is how the dark matter is produced in the early universe. So we have a very beautiful model of cosmology. Can we use it to actually tell something about the dark matter candidates? So can we at least prove how these dark matter particles are going to be produced? And if you allow me a comment, that's something which is very interesting. We have no idea why the dark matter, so about the baryonic part of the universe, right? Protons, electrons, photons, we have no idea how they were produced, why they are as abundant as they are. We have no idea. This is related with the so-called the mystery of the baryon asymmetry in the universe. Even if you fix the photon density, you don't know why the baryons are so abundant. However, in the theoretical community, there is this prejudice that somehow we have to find a dark matter candidate that leads to the observed relic abundance in a natural way. And that explains why the dark matter, why the abundance of dark matter is only 5 times larger than the abundance of baryonic matter. But we don't understand the baryonic matter. So it's very interesting, this condition. It is somehow paradoxical. So we have plenty of ideas for what dark matter can be, and they have a vast range of masses and vast range of properties The most interesting properties for us are the mass and the interactions with the standard model particles, because these interactions are going to create all effects that I have not described you in my introduction of dark matter, right? So they are going to be able to produce photons, or they will be able to be produced in the early universe. They will lead to signatures. So far, everything that I've explained to you is consistent with the existence of the boring dark matter candidate that stays there and only feels gravity and doesn't do anything else. Luckily, the imagination of theoretical physicists is just providing with a much more colorful playground where we will see a wealth of different effects, and we will have to look at the universe in very funny ways to search for this dark matter. So that's everything for today. Questions?